chances are at some point you've mixed up a solution with water, whether that's mixing up Kool-Aid or lemonade or other powdered drinks, or you've needed to dissolve salt or sugar into water in order to make something. But what is it about water that allows this to happen? Well, today we're going to look at polar molecules, specifically at water, and what makes it a polar molecule and how that impacts how things dissolve or don't dissolve in water. We're also going to explore a little bit of chemistry math, talking about how it is that we balance chemical reactions. So let's get started. Hey guys, welcome back to Making Sense of Chemistry. Today's video follows along with Supplement Week D from the Chemistry in the Kitchen curriculum from Guest Hollow. But even if you're not taking that specific course, if you're just taking another general chemistry course, these videos are designed to help you understand different chemistry principles a little more simply using things you can find in your kitchen and experimenting with food. As someone who studied chemistry in college, I understand that this can be a confusing subject, and so we're aiming to help you understand these basic principles in a way that just makes sense. So if you are looking for specific chemistry topics, look in the title of the videos, but you can also look down in the description box to see what types of things we're going to talk about. Today I want to start by talking about polar molecules and specifically water. We've learned that water is H2O, which means we have two hydrogen atoms that are bonded to one oxygen atom. And these are covalent bonds between the atoms, which means that electrons are being shared in order to give all of the atoms full valence electron shells, making them happy and stable. But while they are sharing electrons, they're not exactly sharing them equally. You see, hydrogen's pretty small. It only has one proton in its nucleus, whereas oxygen has 8. And so oxygen has more of a pull, more of a positive charge in its nucleus, and so it pulls electrons to it more strongly than the hydrogen. Think of it like sharing with a sibling, right? I'm an older sibling, and there were plenty of times where my mom would hand me like a cookie or a brownie and say, hey, split this up and share it with your brother. And while I probably should have cut it exactly in half and shared it that way, did I usually cut myself a slightly bigger piece? More often than not, yes. Because I was the bigger sibling, right? I had a stronger pull on that item. And it's like that with these electrons. So while they are being shared, they tend to be pulled more towards the atom that has a larger nucleus or a stronger positive charge in its nucleus. What does this do to the molecule overall? Well, while water is not an ion, it's not positively charged or negatively charged overall, it's neutral. It means that the oxygen end of that molecule will act as if it has a slightly negative charge, whereas the hydrogen end of that molecule will act as if it has a slightly positive charge.
Okay, let's go ahead and pause me looking awkward here for a moment because it's actually a little more complicated than that. Let me explain. You see, a polar molecule has an uneven distribution of electron density, creating a positive and a negative end or a dipole. This occurs when atoms of different electronegativities form a covalent bond, leading to an unequal sharing of electrons. We can see this trend on the periodic table. In general, electronegativity will increase across a period, that is from left to right on the periodic table, due to the increasing nuclear charge and a decreasing atomic radius. So the number of protons in a nucleus will increase as we go from left to right. So we have a stronger positive charge in the nucleus. And the atomic radius gets smaller because that charge pulls those electrons closer, making the atoms smaller. So a combination of a stronger nuclear attraction and a smaller atomic size gives us a stronger attraction for more electrons, making it more electronegative. However, as we go down a group, so from top to bottom, we see electronegativity decrease because we have larger atoms that have more electron rings or electron shells. And those inner electrons are providing a shielding effect. They are protecting those valence electrons from the full force of this bigger nucleus. And that means overall there is a less of an attraction for more electrons and decreased electronegativity.
This is really important because it allows other polar molecules or things that will break up into ions to be dissolved into the water. Let's look at salt, for example, sodium chloride. This is an example of something that has ionic bonds between the sodium and the chlorine, and when it's dissolved in a solution, they actually will break apart into ions. We'll have sodium and chloride floating around. Sodium will have a positive charge because it donates an electron to the chlorine, and then the chloride ion has a negative charge because it's gained that electron. Now, what do you think is going to happen? What will be attracted towards the oxygen end of a water molecule? The sodium, because it has a positive charge. And then what will be attracted towards the hydrogen end of the water molecule? The chloride, because it has a negative charge. Now, we can actually impact how this will dissolve in water based on the amount of energy we add to the mixture. We add energy by changing the temperature. As we start to heat up water, there's more energy being added, which moves the water molecules faster. They're starting to really bounce around, and that will allow it to mix with the salt faster than if we mixed it with, say, cold water. And we're going to demonstrate that here in a minute and show you what's happening there. But there are other things that we can dissolve with water too. Sugar, for example. Now, sugar is not an ion. It's another molecule that has lots of covalent bonds. However, just like with water, there are some parts of the salt molecule that will act slightly polar. They'll act slightly more negative or slightly more positive, which means that we can dissolve them with the water. And the sugar molecules, while they're not going to break apart into different ions, they'll be attracted towards different ends of the water molecules, allowing us to dissolve them. Now, these are not reactions where we're going to be creating brand new molecules. We're not mixing water and salt and creating something new. We're not mixing water and sugar and creating something new. They're simply mixing together in a solution. If I were to let salt water sit for a couple of hours and maybe the water evaporates, what's going to be left? Salt's going to be left. If I were to mix sugar and water and it dissolves and then I just let it sit for a couple of hours, what's going to happen? That solution eventually will break up. Now let's look how changing the amount of energy in water impacts how things dissolve. I have 3 glasses of water here. One, I've allowed some ice to melt in, so it is cold water. I have room temp water, and then I have water that is a little bit on the hot side. I just microwaved it for about a minute. I am going to be mixing salt into all 3 of these, and I should see that salt dissolve in each of them, but I want to see in which one does it dissolve the fastest. So all you have to do for this is choose the amount of salt that you're going to add to each glass. So here I'm just going to take part of a spoonful and I'm going to add it to my first glass, my cold water. So it's going to go ahead and start to mix together and I'm going to stir it up. And you could set a timer if you want to, so that way you could be really scientific about this and see how long does it take for that salt to dissolve. I'm going to do the same thing with my room temp water and then with my hot water. What you should notice is that the hot water solution dissolves the salt the fastest and the most completely. That is because there is more energy in there. The water molecules are moving faster in the hot water. They're really bouncing around, causing it to interact with those salt molecules that are breaking apart into ions more quickly and more rapidly. So there is more chances of water hitting a piece of salt, right? Hitting a bit of that sodium or that chloride and forming that solution. Okay, so I've done my 3 mixtures and sure enough, it took almost no time for the salt to dissolve in my hot water. And even with my cold water, while it's dissolving, it didn't even dissolve quite all the way. It took a lot more stirring to get this to happen. And again, if I were to just leave these sit and let the water evaporate out, I'm gonna see that salt's gonna reform and it's gonna be left behind. Now, an important thing to know about solutions is that polar molecules like other polar molecules and polar molecules like ions. However, not every molecule is polar. There are lots of things out there that are non-polar. There is an equal balance of the electrons throughout the molecule. There is not one end that is acting slightly negative and an end that's acting slightly positive. They simply are neutral all the way around. So we call those non-polar molecules. And a great example of something that is non-polar is vegetable oil. In fact, vegetable oil, canola oil, most of your other oils. So these are non-polar molecules that make this up. Well, if we have a non-polar molecule and we have polar water, what do you think is going to happen when we mix the 2 together? Well, let's see. So you can see that the oil separated almost immediately from the water and it's formed a layer on top of the water and the water is down below. Why does it do this? Well, water is polar and oil is not. It's non-polar. And in this case, opposites do not attract. Nonpolar molecules do not want to mix with polar molecules. That's why when you try to mix together oil and water, they will always want to separate. They just don't want to be around each other.
Okay, let's pause me awkwardly again here because I want to highlight this about nonpolar molecules. So a nonpolar molecule is one where electrons are shared equally between the atoms, resulting in no significant difference in charge distribution across the molecule. In other words, the pull of the electrons is equal everywhere you look in that molecule.
So to sum this part up, some molecules are polar. That is, electrons are pulled more towards one atom in that molecule than another, giving it a slightly negative charge on one end and a slightly positive charge on another end, even though overall this is a molecule and not an ion. That means that it can readily mix with other polar molecules or with molecules that break up into ions. However, they will not mix well with things that are nonpolar. Molecules that have no charge or no pull one way or the other, they are simply neutral all the way around. Now, a great way to expand this experiment is to try testing different things dissolving in water. Make predictions about what things you think are made up of polar molecules or molecules that will dissolve into ions, and then test it by trying to dissolve it in water. You can grab anything from your kitchen: lemon juice, sugar, salts, apple juice, whatever you can find. And then again, make that prediction, that hypothesis about what will happen, and test it by trying to mix it in with water. You could also look at how fast things dissolve by, again, adding or taking energy away from the solution. Heat it up to add more energy. How much faster does something dissolve that way versus if you were to use ice water, for example? So again, lots of different ways that you can experiment with this. Next, I want to talk just a little bit about chemical reactions and how it is that we balance them out. Now, this is not part of the Chemistry in the Kitchen course. However, for those of you who want to get a little bit of chemistry math in, learning how to balance equations is pretty important. So let's go over to the whiteboard and take a look.
What do we mean when we talk about balancing a chemical equation? Well, let's start with a pretty simple one. Hydrogen normally occurs in the environment as H2, or a hydrogen bonded to another hydrogen, or a hydrogen gas. Now, oxygen normally occurs as O2, oxygen bonded to another oxygen. But these will react together and they will form water, H2O. Now, something I want you to pay attention to are these subscripts here. So you see there's a 2 there, there's a 2 there, and there's a 2 there. The subscript tells us how many of that atom are present in that molecule. So hydrogen, H2, for example, means that there are 2 hydrogens. O2 means that there are 2 oxygens. H2O means that we have a hydrogen and an oxygen and another hydrogen. We have 2 hydrogens. Because there is no subscript here by the O for oxygen, that just means that there's 1. We don't write H2O1. That seems a bit silly. So we just leave it as O. So again, this is how many of an individual atom are present in that molecule. Now, with a chemical equation, we have to have things balanced on both sides of this equation, or on both sides of the reaction. It means the same number of each individual atom that are present on one side of the reaction have to equal the number of that atom on the product side of that reaction. So in this example here, let's look at hydrogen. Well, there is the subscript 2, right? So that means we have 2 hydrogens. And there is a subscript 2 after the oxygen, which means there are 2 oxygen atoms. Over here on the product side, we have 2 hydrogens, but we only have 1 oxygen. Something is not balancing out here. That means that we are going to have to figure out how many of each of these molecules we need to have on each side of the equation to make this balanced. We can show the number of molecules that are in the reaction by adding a number in front of the molecule name. So that means we're going to be adding to the front of these here to show how many of that molecule there are. We are not going to be changing the number of atoms that are in the individual molecules. We're just going to change the number of molecules that are needed to make the reaction happen. So in this case, let's look at how we can balance this one out. Right now, we can see that we have 2 oxygens on this side, but only 1 over here. That means that we're going to have to add to this side in order to make this reaction balanced. So let's say that we put a 2 here in front of this H2O. Now, how many of each of these atoms are present on this side? Well, since we have 2 of the H2s, that means that now we have 4 hydrogens over here. And we have 2 of the oxygens. Okay, so now I can see that my oxygens are the same on both sides. However, now I only have 2 hydrogens over here, but 4 over here. It's not balanced. What can I do to fix this? Well, what happens if I put a 2 in front of my H2? Now I have 4 hydrogens, and you can see that it's balanced. I have 4 hydrogens on either side of the reaction and 2 oxygens on either side of the reaction. This means I have to have at least 2 molecules of the H2 to combine with 1 molecule of the O2 to make 2 molecules of water. So the big thing to remember is that by adding a coefficient or a number in front of a molecule name does not change the number of atoms in an individual molecule. I am not combining 4 hydrogens together here. I simply have 2 individual molecules of the hydrogen gas. I don't have 4 hydrogens and 2 oxygens all bonded together. I have 2 molecules of water that are being created. The subscript is what tells me how many of the individual atoms are present in that molecule, whereas the coefficient in front tells me how many of those molecules are present. Now, at this point in math, you've probably learned about least common multiples, and this can be really helpful when learning how to balance chemical equations because essentially what you're looking for is the least common multiple between the 2 sides of the reaction to figure out how many of each molecule you need to have. But let's practice with another one, maybe one that's a little more complicated. All right, let's look at a second example. Here we have a reaction that has a molecule that consists of 2 atoms of iron combined with 3 atoms of oxygen. So that's one molecule. It reacts with carbon to give us iron and CO2, carbon dioxide. Let's start by breaking down how many of each individual atom are present on each side of this equation. On the reactant side, we can see from that subscript 2 that we have 2 atoms of iron, we have 3 of the oxygen, and we just have 1 of the carbon. Over on the reactant side, we have 1 iron, 1 carbon, and 2 oxygen. Now, what I like to look at first are the things that have the biggest numbers on them. That helps me with balancing my equations faster. So I'm actually going to start by looking at these oxygens here because we've got 3 on one side and 2 on the other. I need to go ahead and think about what's the least common multiple of 2 and 3. Now, the least common multiple of 2 and 3 would be 6, right? So what do I have to multiply 3 by to get 6? I have to multiply it by 2. So I need to start by giving myself 2 of this molecule. That means that I'm going to have 2 times 3. I'm going to have 6 atoms of oxygen total on this side. What do I have to multiply 2 by to get 6? I have to multiply it by 3. So now I have 3 times 2. I have got 6 atoms of oxygen. This also changes on this side the number of carbons that I have because now I have 3 times 1. I have 3 atoms of carbon. On this side, it changes how much iron I have. I have 2 times 2, so I have 4 atoms of iron. So my oxygens are balanced out. I'm good to go on those. I don't have to worry about the oxygen at the moment. But let's look at what's no longer balanced. Well, my iron is no longer balanced. I have 4 iron here on the reactant side, but only 1 on the product side. How can I fix this? Well, if I have 4 irons on the reactant side, now the iron is balanced out. What's still left? My carbons. I can see that I have 3 carbons on my product side, but only 1 over here on my reactant side. So I'm going to change this by adding a 3 in front of it. And now everything balances out. I've got the same number of irons on both sides, the same number of oxygens on both sides, and the same number of carbons on both sides. That means that I have to have 2 of this molecule react with 3 of the carbon atoms. It will give me 4 iron atoms and 3 of the carbon dioxide molecules. And so this is an example of balancing a chemical equation. Now, these can get pretty complicated depending on how big your equation is, how many things you're reacting together, but the principle remains the same. You start by listing out what you have on your reactant side, what you have on your product side, and then start to look for those least common multiples from one side to the other, and just go through and change them one at a time and looking at what it is you need to adjust next to balance them out.
All right, that's it for today's video. Hopefully that helps you understand a little bit about balancing chemical equations and the difference between polar and nonpolar molecules. Next week, we will dive into officially week 1 of the Chemistry in the Kitchen curriculum, making the highlighted recipe for the week and talking about what kind of chemistry we're actually observing as we make that dish. Thanks so much for joining me today, guys. Remember to think like a proton. Stay positive.